Okay, I think we can get started. We're happy to have Dr. Han-Lee Liu here at HAO. He got his PhD at the University of Michigan in 1996 and came to NCAR and HAO right after that in 1997. He came as a postdoc and joined the scientific staff in 1999. And he's interested in many aspects of geophysical and geophysical fluid dynamics. And he's the lead of the Thermosphere Ionosphere extension of the whole atmosphere community climate model, WACCM. And he will tell us about atmospheric waves and upper atmospheric variability.
Thank you, Mark, and thanks for coming. And so today, my title of my talk is Atmospheric Waves and its relationship with upper atmosphere variability. And this is the outline of the talk, where I'm going just to introduce the topic by briefly talk about the atmosphere waves we're interested in, the wave sources and their propagation. And the focus will be on the wave impacts in the upper atmosphere, specifically the variability due to planetary wave and tidal interactions and their effects on the ionosphere and the thermosphere, the research I've been doing in the last few years. Another thing is we think it's may become more important is we want to study the predictability of the upper atmosphere and their relationship to atmosphere waves. And then a summary and pointing out some outstanding issues. And this is very basic stuff. We know that the atmosphere state is essentially in the vertically it's in a hydrostatic equilibrium state. And horizontally, it's a geostrophic equilibrium, at least for extratropical and high latitude. And when you perturb around that state, you can generate waves that can sometimes propagate into the middle upper atmosphere. And here are some list of the most common waves we're dealing with most of the time. And there are plenty of reasons for why we study them, why they're important. And one of the maybe more important reason is that these waves, the internal waves, grow exponentially with altitude to compensate for the density decrease. So the perturbations in temperature and wind become large when they get to the middle upper atmosphere. And that can lead to instabilities, among other things, convective or shear instabilities. And the temperature perturbation can modulate the chemical processes that are temperature sensitive, and also physical processes like the Lagrangian cloud. And for wind, they can induce strong advection, large wind component. They can introduce strong advection and also fast transport, and also produce dynamics and chemistry coupling through transport, and also cause disturbances in thermosphere and ionosphere, which we'll discuss more later. Another thing is the instability, of course, will kick up turbulence, and that can have implications for the mixing and transport of constituents. So another important aspect for wave impact is that they can interact with the mean circulation. So we know that in the stratosphere, mesosphere, and lower thermosphere, the circulation can be modified or even determined by the various waves. And we know that in the stratosphere sudden warming event, planetary wave can strongly change the circulation pattern. And the equatorial waves can drive quasi-biannual oscillation and semi-annual oscillation. And for this study, we rely pretty heavily on numerical models, given such a complex system. We're going to use two models here. One is the NCAR time GCM model. That's the thermosphere, ionosphere, mesosphere electrodynamics model developed by Ray Robo and his colleagues over the last few decades. And I'm glad to see Ray today, sitting here. And in the model, the tides are specified using the GSWM model developed by Maura Hagen. And that's based on more of the climatological heating. And the lower boundary, we can specify the lower boundary using either reanalysis data or idealized, for example, planetary waves. And gravity waves, of course, in such a global models are parameterized. And here in the following studies, we're going to mainly use this model for deterministic and mechanistic studies. Another model we're going to discuss is the WACCM model, the whole atmosphere community climate model with the thermosphere extension. And that can self-consistently resolve the dynamical, physical, and chemical process down to the troposphere, to the surface, though the ionosphere part, the electrodynamics, we're still working on. And the thermosphere part of the model has been recently released as one of the atmosphere components of CESM. And here in this study, we're going to use 10 years of the WACCM simulation trying to statistically study the tidal and the wave variability. And these are under perpetual 2000 conditions, which is a well-controlled solar max condition, and also the geomagnetic condition. We set it artificially to a very quiet condition. And this simulation does have a cyclic nudged QBO. And in principle, the wave sources are pretty well known, but that doesn't mean it's well represented. Actually, there are still some problems. For example, generally speaking, the atmosphere tides in both models sometimes could be a little bit weak. And planetary waves, some of the planetary waves may not be well represented, but in general, climatologically, they're very reasonable. And gravity wave is a very stiff problem because it spans a large spatial and temporal scale. It's always stiff for global models. The good news is that with the development of high-resolution global models, things are becoming more convergent with observations. So that's kind of encouraging. And the key thing in wave propagation is the wind. If we look at the theories of the wave, we find that the wind affects the waveguide, affects the existence of critical layer, and also the wave amplification due to instabilities. This is the PV gradient, and that's closely tied to the wind structure both meridionally and vertically. So wind plays a very important role in determining the wave propagation and wave variability on different timescales. So here's an example of the wave variability. This is a quasi-2-day wave as observed from Hardy. And this is time and amplitude. And you see that for quasi-2-day wave, usually it peaks in the January-February time period. And there's a secondary peak usually after the summer or the June solstice in July and August. And for the 5 to 7 day wave, there's also a very distinct time or annual variation, which usually peaks before and after equinox. And using models, we can determine that the cause of these variations are related to the things we just mentioned, the wave guide, critical layer, and also amplification due to instability. Another very important wave impact is the transport, because as I mentioned earlier, the large waves can induce a very strong horizontal transport or even vertical transport. And here is an example, a recent study by Yue. He used a time GCM and found that in combination, quasi-2-day wave, a strong quasi-2-day wave in combination with tides can cause very large and fast meridional transport. If he released a tracer in the MLT region, the tracer can be transported from mid-northern latitude to Antarctica in a few days. And that provides a plausible explanation for the observed shuttle plume transport when the shuttle plume is released. That can expand, and from the emissions, you can see that they can propagate or transport it into the southern hemisphere, high latitude, in a couple of days. And another impact, as I mentioned earlier, is the wave mean flow interaction. I remember 6 years ago when I was giving this special colloquium, our director at that time, Michael Knoker, very correctly pointed out the importance of QBO in regulating climate variabilities in both lower and upper atmosphere. And he challenged us to have a working QBO in WACCM, which we did. This is done by recognizing the importance of the inertial gravity wave in the atmosphere. So we developed and implemented inertial gravity wave module. And this is the zonal, mean zonal wind, kind of for decomposed from a 155-year WACCM simulation. And you can see we're able to successfully reproduce QBO with a period peaking around 28 months, with sideband ranging from about 22 months to 34 months, quite consistent with the observed QBO feature. This is just a wavelet analysis, again showing the variation of the QBO period. It peaking around 28 months, but varies around. And using the model, we can also study the control of the extra tropical and high latitude circulation. So here is the composite difference between the easterly QBO phase and the westerly phase. So where we see that during the easterly phase, the polar winter stratosphere jet is much weaker than the westerly phase, which is reproducing the Houghton-Tan relationship in the model. And then in the MLT region, you can see also there are quite significant modulation of the circulation there. And also the model, this is from the cyclic QBO simulation for WACCM-X. We can see the model was able to reproduce the modulation of tides. In this case, it's semi-diurnal migrating tide, and which shows a peak in the easterly phase, a larger peak in the easterly phase, and a weaker peak in the westerly phase. And this is consistent with observations, for example, the Tidal observation or Tidal analysis recently done by Chen Wu. Another important impact is that the planetary wave forcing and its global response, or whole atmosphere response. In this study, using the coupled time GCM and CCM3 model, we found that with during the SSW, with the planetary wave forcing, it can induce strong changes in the upper atmosphere, including mesosphere heating, cooling, and thermosphere warming, and the change of phase at lower latitude, which is from the simulation we can tell that these are mainly due to the anomalies induced by planetary wave and also gravity wave during the warming process. And this kind of anomaly or the change of the circulation structures are also seen in observations. This is a recent paper done by Bo Tan. He analyzed the SABRE data. What shown here is the kind of a correlation map. This is latitude and altitude. He correlates the temperature anomaly in different regions with the stratosphere temperature in the polar region. And he found a very similar positive correlation in the stratosphere, positive correlation in the thermosphere, and negative correlation in between, and then phase change at lower latitude. And actually, this is quite robust even during times without any stratosphere warming. It's same correlation pattern, even though the magnitude may be different, but the correlation pattern is very similar. And this correlation patterns are produced also in WACCM simulations. And then we can extend a little bit further upward with the WACCM-X and this same kind of idea. And apart from the lower middle thermosphere positive correlation we see here at high latitude, we also see some kind of weak but still statistically significant positive correlation at low latitude in upper thermosphere, which could be due to a downward branch of the circulation change there. And there are also observational evidence for thermosphere and ionosphere responses during SSW. Here is work by Goncharenko and Zhang. They take the radar measurement at Millstone Hill, which is at mid-latitude. And they measured the ion temperature from 2 years. This is a monthly mean difference from 2008 and 2007, where 2008 there's a strong warming. And this is altitude and local time. And apart from seeing this kind of warming in the lower thermosphere and some kind of cooling, if you average out, maybe there's amounts to a cooling in the upper part. What's intriguing is that they see a very clear semi-diurnal signature, and even maybe a terdiurnal signature in the lower part. So, and then that generates a lot of interest, so much so that people decide to have some campaign studies. And then they captured the 2009 warming, which is very strong. And there are some further evidence that the ionosphere is changing. So here are GPS measurement of total electron contents. And this is under normal conditions or mean conditions for local morning for the American sector and local afternoon. And this is during the warming or shortly after the warming of 2009. And they see a very large enhancement of the EIA in the morning and some decrease of the TEC in the afternoon. And this is very clearly seen in this time plot. And if you look at the periodicity, it's again very close to a semi-diurnal period. And corresponding to that, there's a large change in the vertical drift. This is a vertical drift measured at the magnetic equator at Hikamaka. And in the morning, there you see this a very large enhancement of the upward drift. And in the afternoon, there's a downward drift change. And so all this kind of point to two things. One is it shows that maybe the tide must play some important role here. And also because SSW is a period when planetary wave changes very significantly. So the tidal and the planetary wave interaction may play a very important role. And actually that study, the tidal planetary wave interaction, dates back maybe 2 decades when in early 90s, Titelbaum and VL, they showed using a very simple model that they can explain some of the observed frequencies using tidal and planetary wave interactions. And then in 2001, Hagen and Robo, they used a time GCM simulation and demonstrated that with the diurnal migrating tide and planetary wave 1, they can generate a very strong diurnal non-migrating tidal component, a westward 2 non-migrating tidal component. And that has been confirmed from observations. In this paper by Lieberman et al., they found that very strong correlation between the product or the child wave, the W2 non-migrating tides, with the planetary wave 1. And also from ground-based observations, you often see this very large tidal variability. And this is taken from observation by Joe Shea at Colorado State University using LIDAR. And they showed the diurnal temperature and wind, zonal wind, in a period of 9 days of continuous LIDAR measurement. And you can see that from day to day, you can have very large jumps or decreases of diurnal component. The diurnal temperature can jump by 3 times, and then decrease after that. So, and at that time, we looked at the satellite observation, and there's some evidence of planetary waves, a transient planetary wave for that time period. This, by the way, this is a September, October time period. And then we decide to follow what Maura and Ray has done and prescribe a transient planetary wave in the model. And indeed, if we look at the structure of the diurnal temperature and diurnal zonal wind, this is a latitude height, we see very strong, large changes. It's above about 90 kilometers. The structure of the diurnal tide, total diurnal tide, changes very significantly. And if we seek out the location of CSU for Collins, we do see very large changes similar to those observed in the LIDAR observation. So this kind of demonstrates the feasibility of producing very large tidal variability within a short period of time, and through the nonlinear interactions. And also, one interesting thing I want to point out is that in the region, in the E region, between 100 and 120 kilometers, where the dynamo can play a very important role, you do see very large changes. So indicating that this may also affect the ionosphere, electrodynamics. So that's kind of a motivation for more recent study, where we picked a time period when the planetary wave is very strong, namely during the northern winter season. And we prescribe an idealized planetary wave 1 in this case, and launch it from the lower boundary of the model. This is, again, latitude height. And you can see that planetary wave does propagate upward, though it's mainly trapped below the low thermosphere and to higher latitude because of critical layer. So this component itself may not have a very strong impact on the ionosphere. But if we look at the wave other tidal components, for example, the planetary wave, the migrating diurnal tide, semi-diurnal tide, and this non-migrating component, semi-diurnal westward 1 component, they all change at different latitude, low latitude, or high latitude, and in E region or even in F region. So these are important because, again, these are region where the wind can disturb the dynamo and cause electrodynamics changes. So then we looked at the vertical ion drift in the model. And here, the dotted line is from the base case simulation over January to February time period. And you can see it's very stable because it's just a climatological tides. And then when we introduced this planetary wave, we began to see some perturbations. And this is the difference between the two. And they show a very clear diurnal and semi-diurnal signature. And this is the map of the vertical drift, longitude, latitude, in the case without the base case, without planetary wave, and then with planetary wave, and we see a large vertical drift change extending from low to high latitude. So then what we decide to do is trying to look at the contribution from different locations and different wave components. Taking advantage of the kind of the linear nature of the electric potential equation or the wind dynamo equation without considering the feedback from conductivity. We can decompose by altitude or wave components or latitude. So first we look at the E and F region. So in this experiment, we replaced the neutral wind in dynamo only in the E region by base case, either the meridional or zonal component or both components. And then we found that the perturbation we saw during the event either weakened or disappeared. And then we do the same thing with the F region, and we do not see a lot of change. So this strongly indicates to us that the E region wind dynamo is what's causing these changes during the planetary wave event. And then we look at the E region neutral wind. This is a zonal wind and meridional wind. So an important feature here is that at places you can see very large zonal gradient of the wind, either in zonal or meridional components. And these are important because this determines in the dynamo region, this determines the Hall of Patterson current. And the gradient will translate to divergence or convergence of these currents, which will indicate the buildup or depletion of polarized electric charges. And indeed, if we look at the electric charge and associate that with the electric field set up by those polarization charges, they are very consistent with the vertical drift change we see in the simulations. So another thing we looked at is try to understand the contribution from different wave components, where in this in-time GCM model, we can introduce the wind, only one or few components at a time, and try to understand the contribution from this wave components. So the solid line is if we only include in the model the background plus the diurnal or migrating tide. And that produces the kind of climatological feature that in the morning you have upward drift, a weak downward drift in the afternoon. And actually, if you only include the migrating tide, it produces a quite strong pre-reversal enhancement, even under this solar minimum conditions. And then when you introduce the SW2, the semi-diurnal migrating tide, the sign of the vertical drift at the equator, this is our equatorial region, the sign flips. So that tells us that the semi-diurnal tide actually is contributing in an out-of-phase fashion with, compared with the DW1. And then if we only include the SW1, the non-migrating component, then we see a very large enhancement around dawn. This is a local time, so it's 5 in the morning. And then if we only introduce the planetary wave, the original planetary wave kind of launched from the lower boundary, it doesn't change much. So again, confirming that the planetary wave doesn't contribute directly to the vertical drift. So these are the maps of these contributions from DW1, morning upward drift, weak downward drift in the afternoon, pre-reversal enhancement. And this is from SW2, the migrating diurnal tide, and you can see indeed they contribute in an out-of-phase kind of fashion with, compared with the DW1. And then this is the SW1, non-migrating component, and they enhance the morning drift, both negatively or downward or upward. And then we look at the E-region wind from these different components. And this is the migrating component, and this is meridional wind. And that is in the southern hemisphere where the wind peaks. It's about in phase with the SW1 component. So it's not surprising that their contribution to the vertical drift is also constructively interference. And then this is the semi-diurnal tide, and in the morning, it does show some kind of out-of-phase behavior with the migrating diurnal tide. So then what we do next is we try to understand the latitudinal distribution or contribution from these different components. And one way to do that is a bit similar to the kind of the green function idea, is to just introduce wind at one single location. In this case, it's only one single latitude. And we run through all the latitude and try to quantify their contributions. So this is an example. If we just take the wind, the neutral wind from this component, the SW1 component, and at only one single latitude, and look at their global response of the vertical drift, we can see that this is from just 52 degrees south, equator, and 52 degrees north. And we can see that among this, the largest global response comes from the wind we introduced at 50 degrees south. And if we go through all the latitude, then we can count them and then decompose the drift at one particular location, in this case at low latitude, and project them onto a different latitude and look at the latitude contribution. So for example, the SW2 component, we can see that in the morning, a lot of the contribution comes from higher latitude at around 52 degrees, and even in the northern hemisphere, and sometimes the two are in phase, and sometimes they could be out of phase. And in the afternoon, the low latitude may contribute to the vertical drift of this vertical drift here. And then if we look at the wind dynamo from the SW1 component, we also conclude that very significantly the contribution comes from mid to high latitude. And what this was doing is probably because the strong cross-polar flow was producing this, again, the Patterson, set up the Patterson currents, produced the polarized charges and polarized electric field. And then we want to study the solar dependence, and we run the same experiment, but the only thing changed now is we changed the solar activity. And then we see that, especially in the morning, the vertical drift change at the down was reduced almost by half. And on the other hand, the pre-reversal enhancement during solar max conditions are usually more prominent, and they are modified by the planetary wave. And this may have some interesting and important implications for the, for example, the study of spread F. And the main change between solar max and solar mean is the conductivity. And for example, the peak Patterson conductivity in the F region can increase by almost an order of magnitude. So we did some further experiments trying to figure out, try to isolate different factors affecting this. So in these experiments, we only change the conductivity. So in general, if we increase or decrease the conductivity, the Patterson conductivity in the F region, then we significantly increase the morning response, namely the response due to the planetary wave and tidal interaction, and at the same time decrease the response or kind of eliminate the pre-reversal enhancement. And the reverse happens if we increase the F region Patterson conductivity. So what this suggests is that seems the F region Patterson conductivity was suppressing the variability at down, probably by shorting out the E region dynamo effects. And at the same time, it can enhance the variability of both the PRE and the variability of PRE, the pre-reversal enhancement. And so this I've already shown, this is what's observed. And it seems from the model, we can reproduce some of the features observed in this campaigns, namely that you have a change in the vertical drift. Morning, you have an upward drift, and afternoon, you have some downward drift, and then the TEC change accordingly. But both the magnitude and the phase of the change reproduced in these idealized simulations, they are still different. They are quite different from the actual observations. And more recently, Tim Flowell and their group used the WACCM, the NOAA whole atmosphere model, with the data simulation for the meteorological, using meteorological materials. And then they feed the simulation and use that to drive the CTIP-E, and they get electrodynamics changes in the ionosphere very similar to the observed change. And what they found is that in their simulation, the semi-diurnal tide and the terdiurnal tide can play a very important role there. So both the mechanistic studies and also the case studies kind of show strong evidence that the planetary wave and tidal interaction can produce short-term variability during SSW. So then the question is, because as I mentioned earlier, the time GCM, the tidal source is from basically from climatology, and also the planetary wave is well controlled. So will those understanding we gained from the mechanistic studies hold if we have a more realistic atmosphere? Things are more variable. The wave propagation are more variable. The wave source could be more variable. So that's why we decide to look at this problem using the WACCM Max model. So here is a little bit busy plot. So what I have here is the first row is the temperature at 10 hectopascal in the stratosphere in the polar region. And the second row is total wave number 1 at 1 hectopascal, usually under 60° north. That's usually when they peak, where they peak. And then this is the migrating diurnal tide in the MLT region. This is near 105 kilometers, 10 to the minus 4 hectopascal. And this is at 20° north, which is usually the meridional wind of that tidal component peaks. And this first column is the just 1 month of the simulation, January, one of the Januaries. And then that's the whole year simulation. And then these are from the 10-year simulations. And in January, you can see that there's no evidence of any stratosphere warming. And the planetary wave at that time is quite strong, vary between 1,000 and 2,000 meter geopotential height. And if you look at the diurnal migrating tide, that has large variability from day to day, and quite similar to what we see from the observations earlier. Can jump 3 or 4 times. And if we look at the whole year, actually in February of that simulation year, there's a quite strong warming, and accompanied by this collapse of the planetary wave. But if you look at the variability of the tides, at least at this altitude and location, their variability is persistent throughout the year, and with the magnitude quite similar throughout the year. So sometimes if you just look at, according to this variability, it may be a bit hard to clearly establish any relationship between, say, the variability around, a warming period. And this is just, 10 years. You can see that they do have variability a lot of times, and at the same time, they are modulated on longer time scales by QBO. And these are just some of the other wave components, semi-diurnal tide migrating, D3, and SW1. And all of them shows very large day-to-day variability in the absence of any warming, of course. And again, it's maybe hard to establish a clear relationship just by looking at this between that and, say, stratosphere warming. And so what we did is we did some statistical correlation analysis. And in this case, we just try to correlate the various wave components with the northern winter state. Here, in these 3 cases, we just correlate that with the stratosphere temperature in the polar region. And we see that for DW, and the shaded area, blue shaded area, again, is kind of suggesting statistical significance at 95% level. And for DW1, we mainly see in the southern or summer hemisphere see a modulation pattern, and with increases at some places, decreases at other places. And this is qualitatively similar to what we get from mechanistic models, that the DW1 is usually modulated by the planetary wave. And then in the D3, we see some change in the high latitude, probably due to the waveguide change during the warmer or cold anomalies. And then but it doesn't have any strong correlation at low latitude in the MLT region, where D3 peaks and affects the ionosphere. And for the migrating semi-diurnal tide, there's a very large positive correlation in the southern stratopause region, which could be due to the increase of tidal components. Increase of the ozone during the warm anomaly, and that warm anomaly, the positive correlation can extend all the way to the MLT region. And then higher up, you see some decreases. So this part may be more consistent with what we see from the mechanistic model studies, which doesn't include very good resolution of maybe the ozone change. So the whole pattern may be a superposition of the change caused by ozone transport and nonlinear interaction between the different wave components. And this is the SW1, the non-migrating component. And it doesn't show a lot of correlation with the temperature, but it does show quite significant correlation in the MLT region, especially in the summer side with the PW1, which is not that surprising because we do know that the PW1 can generate the SW1 by interacting with the semi-diurnal tide. And then we did some further lag analysis. This one shows the lag analysis or correlation between SW2 and the temperature, the polar temperature. And we see that they have a pretty good correlation in the MLT region, like what we see in the previous figure, with a peak slightly lagging the peak warm anomaly, so maybe a few days. And then the SW1, the non-migrating component, again shows a very clear correlation with the planetary wave 1, and with almost immediate response in that wave components. And then we looked at the southern hemisphere winter, and of course we know that there are little or there's very few major warming there, and even in this model there are fewer minor warmings compared to climatology when the cold pole problem. This is found by Amal Chandran. He found that in the presence of the cold pole problem, you have usually smaller number of minor warmings in the southern hemisphere. But the correlation pattern actually is pretty robust. Again, shows a very clear modulation pattern for DW1 in the summer hemisphere. Not much going on for DE3, and again for SW2, there's some correlation, pretty robust in the stratopulse region, even though there are little actual warming, but maybe the anomaly will be enough to cause this correlation, and that extend into the MLT region and some negative correlations higher up. And for the SW1 correlation with Z1, the planetary wave, there are some indications of correlation, but it's generally pretty weak for the southern winter hemisphere. So this indicates that even in the WACCM-X with a high variability, you still has a pretty robust or significant feature between these different wave components, suggesting the interaction still play a role, the tidal and planetary wave interaction still play a role in the short-term variability. But we notice this problem that there's a big discrepancy between the timescales of planetary wave change and tidal variability. So this is just copied from previous figures. This is a planetary wave 1 and diurnal migrating tide, semi-diurnal migrating tide. So if you look at the time scale of the planetary wave change, it's more like on the order of a few weeks. But this is day-to-day for tidal components. So that tells us that maybe the day-to-day variability, the very high-frequency variability in the tides may not be explained in terms of just planetary wave and tidal interactions. And this is a kind of same impression we got from this animation. It's kind of a little dark here. So this is a zonal wind from WACCM-X simulation at 50 degrees south, longitude, height, and this is a December. So we can see that lower down, the planetary wave dominant region, you do see variations, but the impression you got is they're much slower than the variation you see at higher altitude. And the differentiation between the short-term and day-to-day may be important because in ionosphere variabilities, we see a lot of day-to-day variability. And this is taken from Richbath and Mandillo, 2001. They showed at mid-latitude, this is at the slough, they have the peak ion density measurement for different seasons, and they show very large variability, and actually the variability around equinox is even larger than at solstice. And of course, many of this can be due to the geomagnetic activity, which causes the variability. But they also conclude that lower atmosphere coupling play a very important role in this day-to-day variability. So then we wonder if this tidal day-to-day variability, as we've seen in both observations and in WACCM-X, can explain some of this ionosphere variability. And also wonder what's the actual cause of the tidal variability, the day-to-day variability. And one thing we can think of is maybe the variability in the source region, or maybe the internal atmosphere variability. As a chaotic system, you always have this. And that's something we looked at a little bit further, which is to look at the internal variability of a whole atmosphere model, namely WACCM. So what we did here is that we run, again, some identical twin experiments for 10 members of WACCM. And you see that they start with a very similar initial condition with a little bit of deviation. And this is a zonal wind zonal mean zonal wind at a particular location in the stratosphere. And you see that after a certain time, about 20 days, things begin to diverge. And this is very common among all model simulations. And if we look, we pick one day and pick two members from those ensemble simulations and do a difference field on the zonal wind, we see that they are strongly regional dependent. This is the latitude and height. And we see that this is in December, that the error growth in the, so we just call this error growth because they're just deviations from the initial error. So the error growth in the summer hemisphere, stratosphere region is very weak. And actually, I think I have error growth curves here. And then in the MLT region, they're much stronger, where the planetary wave or tides are very large. And similarly, if we look at the low latitude region, we see very robust error growth, again, in the MLT region, but not much lower down. And then on the other hand, if we look at the northern winter hemisphere, the error growth is much robust in the stratosphere, where the planetary wave we know is very large. So to understand this error growth, at least we can think of two scenarios this can happen. One is maybe we can call it bottom-up control, where we introduce error and that can manifest or propagate upward and cause error growth at higher altitude. Another scenario is probably a global interaction where, which is very conceivable, plausible, and where the planetary wave or tides or gravity wave, they can engage in feedback interactions at all altitude and cause error growth at all altitude. And it seems that the earlier picture we see in the error growth kind of seems consistent with either of them. So, and the reason this may be important is their implication for forecast or data assimilation strategy could be different. If it's former, then maybe it's good enough to have a good lower atmosphere clamping or a lower atmosphere control. If you can control the lower atmosphere error, then you will get pretty good maybe response in the upper atmosphere. Or if it's the latter, then seems that you have no option but you have to go with the whole atmosphere simulation approach. And this is only consider, I should say, all these experiments I'm going to discuss later, only consider the dynamics, uncertainty in dynamics, not including any uncertainty in chemistry. So chemistry is the same in the model. So then we decide to do some experiments, try to look at this problem. And basically what we're trying to do is to look at the bottom control and see if that controls the error growth in the upper atmosphere. And to do that, we designed some WACCM experiments where we specify a base case. We have a base case, B case, and then identical twin case, A case, where we introduce the initial error. And then, of course, these two, we know that they will generate an error growth. And then we did some additional experiments where we run A, but every delta T time at certain altitude in the lower, near the lower boundary, we specified, introduced a kind of the truth knowledge from B and see what happens. So this is an error growth curve for the upper atmosphere. And the black curve is the original two cases. The error grow after a while. And then this B curve is with the controlled experiment where we introduce the B information in A, or truth in A, every 24 hours and at a specific height at 50 hectopascal. And it's very interesting to see that this very nicely controls the error growth in the upper atmosphere. And then we can change the level of where we specify the lower boundary. And then the error may become larger at 500 hectopascal. And at 700 hectopascal, if you go even lower, you begin to recover the error in the lower, similar to the original case. And then, of course, we can also see what the delta T time, if we introduce it like every 5 days or 20 days, which it's not that surprising that you get more error growth when you increase the time you introduce the truth to the model. So this seems to suggest that, at least in WACCM, this is a mechanism we have for the error growth that mainly a bottom-up control kind of mechanism. And so it may suggest to us that maybe it's okay to if we want to do forecast, we can get by just assimilating results from lower atmosphere, have a good lower atmosphere. But there's one thing that's missing from that simulation, which is in situ generation of gravity waves. As shown by Yamashita et al., you can have very robust wave generation, gravity wave generation in the stratosphere in this case. When the jet is really distorted, you have a very strong gravity wave generation. So then that means you have a wave source in the midair. And so what's the implication for predictability in that case? And of course, you have other scenarios. For example, if you have a wave breaking, the dissipation can exert body force, which can also generate gravity waves, and that can have impact on the wave source too. So there's this recent paper I found very interesting, kind of addressed that problem. So this paper by Engen and Apron, they use this Met Office unified model with a quite high resolution. This is a 50-kilometer horizontal resolution, and it goes up to the lower mesosphere. And what they found is, so with this kind of resolution, they are able to resolve quite a significant chunk of the gravity waves, and that's what they focus on. They focus on the initial kind of error growth, which occurs in the smaller scales, and namely the gravity wave. And what they found is that if you look at this table is error growth rate for different, they changed the various scenarios, different time resolution, different upper boundary, and they look at the error growth in the troposphere, stratosphere, mesosphere, and they saw that there's a decrease in the error growth. So it means there's a strengthening of predictability in the upper atmosphere due to the relative importance or increasing importance in the gravity waves. At least that's their interpretation. And you can see the same thing. This is a time, error growth, and this is a troposphere, stratosphere, and mesosphere. So they didn't do any specific experiments to try to control the error, but at least they got a result of error growth kind of similar to our large-scale studies. So I think I'll end there. It's just a summary of what I said. So from the mechanistic studies, seems the planetary wave and tidal interaction can lead to short-term tidal variability, and that can affect ionosphere variability, especially at the equatorial latitude, but the contribution can come from all latitude. And the complexity of the response may come from different wave components and their spatial structures. And we also see that the response around dawn and dusk will depend on the F-region Patterson conductivity, which in turn depends on solar activity. And then from the statistical studies, we still found some robust correlations between various wave components, suggesting that the interaction is still pretty significant for accounting for short-term tidal variabilities. But the time discrepancy between the planetary wave and tidal variability suggests that there may be more than just a tidal planetary wave variability for the day-to-day variability. And then what's this? That tidal variability could be related to wave source and atmosphere internal variability. And kind of in our error growth experiment, it kind of suggests that it's indeed somehow related to the lower atmosphere, either internal variability or the source. And we found from WACCM at least, the atmosphere waves can enhance predictability in the upper atmosphere. So we think this is another reason why the study of waves is important, because they may play a very important role in the predictability of the upper atmosphere. And there are some outstanding issues that I mentioned earlier that we still are not sure if the day-to-day variability of the tides are really tied to the ionosphere day-to-day variability. And of course, we can think of a lot of other causes. For example, the gravity wave can also play a very important role, which will be reviewed more by maybe in future higher resolution simulations. And as I mentioned here, the gravity wave is barely touched in current models because of the coarse spatial resolution. So some of the important questions still need to be answered, how they interact with planetary waves and tides. And of course, the parameterization may not really represent what's going on. And the seeding of the error growth by inverse cascading, and also very important question for space weather studies is the seeding of ionosphere irregularity. And then, as I mentioned earlier, some of the important, potentially important process is not considered yet in the predictability study, but that's something we should do in the future. And I just want to acknowledge my co-authors on the works cited here. And most importantly, I want to thank Ray Robo, who has created this nice sandbox for us to play with over the years. And thank you.
Questions? Thanks, Hanli. I can get it going by asking what kind of resolution you needed to get to resolve the QBO or to capture the QBO.
The QBO is already kind of captured using parameterization. So we did kind of, I don't know if it's really perfectly resolved, but maybe I can, actually I will use this backup figure. This is a high resolution model. I think their resolution, this is a Japanese group, their model resolution is I think around 50 kilometers horizontal resolution. And they were able to generate a QBO type oscillation in the stratosphere equatorial region. But the periodicity is short. It's kind of 18 months probably. So it's significantly shorter than what you see in observations. So even with a 50 kilometer resolution, you still cannot really resolve it. And actually, what we found encouraging is that this is from WACCM simulations, and the solid line here is parameterized QBO forcing from inertial gravity wave parameterization. And if you add this up, actually, this is very comparable to the mesoscales. If you add up their smaller scale, these are wave numbers. Their smaller scale forcing, they look quite comparable with our parameterized forcing. But what WACCM is missing is if you look at the resolved wave, which supposedly are due to planetary waves, there's almost no forcing at all at different altitude. While if you look at the high resolution model, they have a very, quite a large forcing from the large scale resolved waves, wave number 1 to 11. And so that's why I said some of the planetary wave may still be missing in the model. And also that's responsible because even though now we generate a QBO with reasonable periodicity, the phase is still a bit off, and maybe the missing planetary wave forcing is maybe responsible, partly responsible for the duration of the phase bias in there.
Is the big challenge vertical resolution or horizontal resolution?
Maybe both. Yeah, I think if you really want to resolve the wave, maybe both are important. Actually, the vertical could be very important because a lot of times the inertial wave has a relatively short vertical wavelength. So yeah. And some studies suggest maybe 500 meters or lower is important.
You showed the transport due to enhanced waves of the shuttle plume. I found that really interesting. And I was wondering if you did trajectory calculations at such a high altitude, how much of it would be reversible and how much of it would be irreversible? And then, not only due to the waves, but also the tidal motions. Are they, does the air just go poleward and then back equatorward, or is there some net transport going on there?
Yeah, that's right. So in this calculation, I think it's mainly due to the superposition of different large-scale waves. I don't think there's any randomness introduced. So I think this one is reversible. So what we did in another earlier study, is that we try to kind of emulate this irreversible effects by introducing some random kicks, which we can assume that they are due to random gravity wave forcings. So it's possible that, I don't know, if you run this long enough, if you have a perfect calculation of trajectories, that may go back. But the model itself, as we know, that the transport calculation itself is intrinsically chaotic. And also, it may go back, so if we have perfect calculations, it will go back at a time which is a common multiplier of the two periods. So that's why I think in this kind of calculation, the superposition of different waves, especially if they are not integer multiplies with each other, is important because they will create a situation where it's not easily repeatable, so to say. But I think physically it is important to include some randomness, either due to gravity waves or maybe higher up. I mean, due to gravity waves, especially the dissipative gravity waves, and at higher altitude, it's maybe the diffusion, molecular diffusion will become important. But I think the trajectory model currently, like the ones used in Stratosphere, I don't know if they include any randomness or diffusive processes. That's an important question.
Okay, if I understand it correctly, it seems to me that there's a bit of an inconsistency there. If you have random gravity wave kicks to get you irreversible motion, but then your last study showed that introducing gravity waves made the chaotic divergence go down.
Yeah, that's a good question. Let's see. But I think these are maybe two different chaos we're talking about. They're in the transport calculation. We know that chaotic because just the Lagrangian trajectory is very sensitive to its initial conditions. But I think later the chaotic divergence we talked about later is the general dynamical state. Maybe they are tied at at certain scales, but that's a good question. I need to think a little bit more about it. Yeah, that's right. So if you count every trajectory trying to get the divergence, yes, that will be a good question.
You talked about a lag between planetary wave activity and tidal activity in one of your conclusions?
In the conclusion or the figure, the slide?
Yes, I'd like to see it again to see...
The lag analysis?
Well, I can't remember the figure, but when you speak of the lag between planetary wave and tidal variability, were you comparing the tides at higher level, the tides at higher levels to the planetary waves at lower levels?
Yes, you mean this one?
Well, I can't remember it. I guess I just wondered whether it's possible to maybe ray trace the tides, because it takes a while for them to get from the stratosphere, say, the site of their planetary wave interaction. It takes a while for them to get from there to, say, the lower thermosphere. And
Right.
I just wondered if that could account for what you saw as a lag.
Yeah, that I guess that's possible. Maybe you can even do a simple estimate by using the vertical wavelengths and periodicity, basically a phase speed.
It's tough to do if you use global modes because it's just very complicated. I tried it recently with simple gravity wave theory at the equator, and I came up with about a week, I think, to get from the stratosphere to the to the upper mesosphere.
I see. Yeah.
It was a very crude calculation, though.
Yeah, from this one, definitely it's shorter than that. This is supposedly, if this positive correlation is due to the ozone change, then that's maybe how long it takes for that change to occur. This is at 105 and this is at 30. So it seems the peak lag is about 3 or 4 days. But again, this is a kind of tie a lot of events together. So maybe for the thing you mentioned, it will be good to do a case study. And yeah.
I think we'll do one last question.
So Hanli, the SSW campaigns were pretty much done during the solar minimum. There was a coming solar maximum. Do we expect to see larger responses in the ionosphere after SSW or smaller response?
This at least according to our simple mechanistic study, it seems in the down sector this will be weaker. Actually, that's a good point. At the ICA meeting 2 weeks ago, they showed some Robert Pfaff. He showed some CNOS measurement under extreme low solar activities under low solar activity. The current state is still relatively low, I guess. And they showed that under extreme low solar activities when the CNOS was just launched, they saw a relatively weak wave number 4 structure, but a very strong the upward drift in the morning sector. And then under the the current condition, it's more dominated by wave number 4, and you don't see this morning upward drift or strong morning upward drift. So basically, in our simulation or in our model study, we also see this under solar max conditions, or under higher solar conditions, the morning response is weaker. But what's interesting is that the PRE, of course, under solar max conditions, will be stronger, and they may be subject to the kind of the modulation we see here due to planetary wave or tides. And that's interesting because a PRE may be a very important thing for initiating equatorial bubbles and those space weather events.
I think if you have further questions, you can stick around and ask Hanli later. But thanks, Hanli, again for a nice talk.